Gravity, atoms, and light. These fundamental elements shape the universe as we perceive it today. From Earth to the vast reaches of space, an array of physical interactions and reactions govern cosmic events. Yet, at their core, all these phenomena can be reduced to just four fundamental forces of nature, which dictated the laws of physics from the very beginning of time. Gravity is one of these essential forces, while light is a manifestation of another. By comprehending all four, we can unlock a deeper understanding of reality, spanning from the tiniest subatomic particles to the largest galaxies. In this video, we'll embark on a journey to decipher the mysteries of these forces, exploring their origins, behaviors, and roles in shaping the early universe. This voyage will take us back to the dawn of time, immersing us in the very forces that hold the cosmos together, the four fundamental interactions. As mentioned, four fundamental forces dictate the physics of the universe today. The most evident is gravity, the force of attraction that structures the cosmic web and keeps celestial bodies such as planets and stars bound together. Then, there are the two nuclear forces, one that binds atoms together, and another that facilitates their breakdown. Lastly, we have electromagnetism, the force responsible for an entire spectrum of radiation, including the visible light that illuminates our world. Together, these forces govern the vast range of interactions in the universe, each transmitted by unique force-carrying particles known as bosons, messenger particles that mediate their respective forces. The standard model of particle physics, a well-established scientific framework found in textbooks and taught in classrooms, describes bosonic particles for three of these four fundamental interactions. These are known as the gauge forces, which operate at the quantum level and are thoroughly understood. However, when it comes to gravity, the standard model falls short, offering no explanation for its fundamental mechanisms. To understand gravity, we turn to Albert Einstein and his groundbreaking general theory of relativity, formulated in 1915. This framework, one of Einstein's greatest achievements, has provided the foundation for our modern comprehension of gravity. It has been rigorously tested through empirical and laboratory experiments. However, relativity remains a classical theory rather than a quantum theory, meaning it does not describe particle behavior in the same way the standard model does. Instead of explaining gravity through a force-carrying boson, Einstein described it as the curvature of space-time in response to mass. Despite speculation about the existence of a graviton, a hypothetical quantum particle responsible for gravity, it has never been detected, eluding even the most advanced Earth-based experiments. Because of this, scientists have yet to reconcile gravity's particle-based nature with the three gauge forces outlined in the standard model. Achieving this would require the development of a theory of everything, an ultimate framework capable of mathematically unifying all four fundamental forces. Until then, the field of quantum gravity remains one of the greatest unresolved puzzles in modern physics. Gravity, despite being the weakest of the fundamental forces, is also the most enigmatic. It requires no light, heat, or complex interactions to function. Mass alone is enough to generate a gravitational field. This simple yet profound characteristic has allowed gravity to shape the cosmos for nearly 14 billion years, ensuring the stability of large-scale structures across the universe. Yet, gravity is riddled with mysteries and contradictions that challenge our fundamental understanding. On a galactic scale, approximately 85% of the mass needed to hold galaxies together appears to be missing. This discrepancy has led scientists to hypothesize the existence of an invisible substance called dark matter, which is thought to form the underlying structure of the universe, despite never being directly observed. On even larger cosmic scales, gravity itself appears to be losing dominance. The cosmic web is expanding at an ever-accelerating rate, seemingly driven apart by an unknown force termed dark energy, another mysterious component of the universe that has yet to be identified. These anomalies, along with the absence of a gravitational boson, make gravity an outlier in modern cosmology. Without fully understanding its origins, we remain unable to trace gravity back to its connection with the grand unified force from which it may have emerged. The other three fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, can all be described using the standard model, suggesting they may share a common origin. If this is the case, then at extremely high temperatures, these forces might have once been unified, acting as different aspects of a single, primordial force. Such temperatures would have existed in the universe's earliest moments. At time zero, the infant cosmos likely began as an incredibly hot, dense singularity, where all matter and energy were compressed into a region smaller than even the tiniest subatomic particles. Within a fraction of a microsecond, the universe began expanding and cooling, reducing its temperature as its volume increased. Approximately 10 to the negative 43rd seconds after the Big Bang, the universe's temperature fell to 10 to the 32nd Kelvin, the moment when the fundamental forces began to take shape. At first, there were only two fundamental interactions: gravity, which remains poorly understood in quantum terms, and a combined force known as the electronuclear force. If the electronuclear force truly existed, it was likely mediated by hypothetical X and Y bosons, potentially the true God particles of the primordial universe. Although little is known about their properties, these bosons would have vanished quickly, making way for more conventional particles like the Higgs boson as the universe continued to evolve. By 10 to the negative 36 seconds after the Big Bang, the universe had cooled below 10 to the 28th Kelvin, a threshold beneath which the electronuclear force split apart due to a process called symmetry breaking. This event resulted in the emergence of two new forces, the strong nuclear force and the electro-weak force. While the grand unified force remains a theoretical concept, the electro-weak force, which unifies electromagnetism and the weak nuclear force, has been scientifically validated. This breakthrough, made in the 1960s, was a key milestone in developing the Standard Model, helping to solidify our modern understanding of particle physics. It transitioned from the electronuclear force, initiating the electro-weak epoch of the early universe, a pivotal phase that set off a cascade of events, reshaping the cosmos into something entirely different by the dawn of the next era. As gravity, the strong nuclear force, and the electro-weak force interacted, they generated what is known as a vacuum pressure field. This field triggered a dramatic expansion of the infant universe, propelling it towards the vast expanse we observe today. Beginning at approximately 10 to the power of negative 33 seconds after the Big Bang, the universe underwent a massive inflation, expanding by at least a factor of 10 to the power of 26, comparable to stretching a nanometer to the size of a light year in an instant. By the time the clock reached 10 to the negative 32nd seconds, this phase of cosmic inflation had completely reshaped the young universe while also cooling it to around 10 to the 22nd Kelvin. At this point, the mysterious energy field driving inflation dissipated, giving way to a sea of energy. From this moment forward, the events described by the traditional Big Bang theory began to unfold. By approximately 10 to the minus 12 seconds, the universe had cooled enough for this inflationary energy to condense into a hot, dense plasma, composed of the first fundamental particles of matter, quarks, held together by gluons, the carriers of the strong nuclear force. The strong force was the second fundamental interaction to emerge, following gravity. As its name suggests, it is the most powerful of the four fundamental forces, exceeding the strength of gravity by an astonishing factor of 10 to the 38th power. However, it has an extremely limited range, acting only within distances of about 1 femtometer, the approximate size of an atomic nucleus. This force is crucial in maintaining the stability of matter at the atomic level. While gravity governs large-scale attraction, the strong force ensures that the fundamental building blocks of our bodies neither disintegrate nor collapse into denser forms. Inside atomic nuclei, protons and neutrons are bound together by the strong force, which is mediated by gluons. This bond is vastly stronger than gravitational attraction, forming the foundation for the diverse elements in the periodic table. On a larger scale, the strong force behaves as an attractive force, but when subatomic particles are compressed beyond a certain threshold, it shifts to a repulsive role. This repulsion, known as degeneracy pressure, prevents atomic structures from collapsing under extreme forces. It is also responsible for sustaining neutron stars, dense remnants of supernovae, by counteracting gravitational collapse, preventing them from turning into black holes. Protons and neutrons, classified as hadrons, consist of smaller units called quarks, bound together by the strong force. Around 10 to the power of minus 12 seconds after the Big Bang, the quark epoch commenced, marking the first appearance of matter in the universe's plasma. Over the next second, these quarks began to combine into hadrons, setting the stage for the formation of the universe's first atomic structures. However, before this process could fully take shape, another symmetry-breaking event occurred, resulting in the final division of the four fundamental forces as we recognize them today. As the universe's temperature dropped below 1 quadrillion Kelvin, the electro-weak force split apart, giving rise to electromagnetism and the weak nuclear force. Unlike the strong force, which binds atomic structures, the weak nuclear force plays a role in their breakdown, facilitating particle decay and transformation. True to its name, the weak force is considerably weaker than its counterpart and operates over an even smaller range. This limitation arises from its mediators, the W+, W-, and Z0 bosons, which are significantly more massive than protons, restricting their influence to just 1/10 the diameter of an atomic nucleus. Despite this, the weak force is responsible for some of the most intriguing and vital physical processes, both on Earth and across the universe. One of the weak force's most unique abilities is its capacity to alter the flavor of fundamental particles, enabling their transformation into different types. This is exemplified by beta decay, which includes two primary types: beta minus decay, where a neutron decays into a proton, electron, and an antineutrino, and beta plus decay, in which a proton is converted into a neutron, a positron, and an electron neutrino. While these processes may seem complex, their significance is profound, as they are responsible for numerous natural phenomena, from nuclear fission in power plants to fusion reactions in the hearts of stars. Although the primary energy source of stars like the Sun is the strong force, it is the weak force that initiates the crucial first steps in the proton-proton chain, the dominant fusion process in smaller stars. In more massive stars, the weak force plays an even greater role in the carbon-nitrogen-oxygen cycle, enabling the formation of heavier elements. When such stars reach the end of their lives and explode in supernovae, the weak force once again takes center stage. It facilitates the rapid neutron capture process, a phenomenon that inundates atomic cores with excess neutrons, leading to the formation of the universe's heaviest elements, even beyond iron. Among the weak force's most elusive participants are neutrinos, which become particularly significant during supernovae. When a massive star collapses, its core rebounds against neutron degeneracy pressure. However, this alone does not trigger the explosion. Instead, neutrinos, which usually interact weakly with matter, begin to engage more actively under these extreme conditions. These interactions inject additional energy into the collapsing layers of the star, ultimately driving the explosion that precedes the formation of a neutron star or black hole. This suggests a deep connection between fundamental forces at the highest energy levels. Normally, neutrinos barely interact with ordinary matter, drifting through space like ghostly particles. However, under extreme temperatures, such as those in a supernova, they exhibit behaviors that hint at a unified nature of the fundamental forces under sufficiently extreme conditions reminiscent of the early universe. Around 1 second after the Big Bang, with the electroweak force now fully separated, newly formed hadrons and their antimatter counterparts began annihilating each other. The weak force played a crucial role in converting the resulting energy into a second category of fundamental particles, leptons, which include electrons, muons, tauons, and neutrinos. Unlike hadrons, leptons do not typically experience the strong force, yet during the lepton epoch, the high temperatures of the young universe allowed both nuclear interactions to influence them. As another second passed, the universe cooled further, dropping below 1 billion Kelvin. At this point, neutrinos decoupled from normal matter and began to drift freely through space, forming a background presence that persists to this day. This decoupling likely imprinted a lasting signature on the cosmos, akin to the cosmic microwave background, which provides our earliest observational snapshot of the universe. However, unlike the CMB, which emerged when the universe was nearly 400,000 years old, the neutrino background dates back to mere seconds after the Big Bang, marking one of the earliest relics of the primordial universe. Imagine the groundbreaking discoveries we could make if we were able to capture the cosmic neutrino background, released just 2 seconds after the universe was born. Such an extraordinary glimpse into the primordial cosmos would completely transform our understanding of its earliest moments. Unfortunately, detecting neutrinos has always been a formidable challenge. They interact extremely weakly with matter, and experiments designed to study them require vast, intricate, and costly setups. But when it comes to the universe's oldest, coldest, and lowest energy neutrinos, the challenge becomes insurmountable. The prospect of observing them is far beyond our current capabilities and likely will remain so for the foreseeable future. As a result, this fascinating map of the infant universe, one that could provide definitive proof for much of what we theorize, will likely remain hidden forever, just beyond our reach. For now, the earliest observable signature of the cosmos remains the cosmic microwave background, CMB, the oldest detectable imprint of electromagnetic radiation emitted when the universe first transitioned into darkness. Let there be light. The final fundamental force to emerge, completing the set of 4, was the electromagnetic force. Its influence began to dominate the universe's behavior at the conclusion of the lepton epoch, roughly 10 seconds after the Big Bang. Although not as strong as the strong nuclear force, electromagnetism is responsible for a vast array of energetic processes, including the emission of visible light, the very light we perceive with our eyes. This force governs interactions through electric charge, which can be positive, as in protons, or negative, as in electrons. charged particles create an electrostatic field around them, leading to interactions where opposite charges attract and like charges repel. The movement of these charged particles generates a magnetic field, which, while distinct, is closely linked to electric forces. These electrostatic interactions serve as the final binding mechanism in atomic structures. While the strong force keeps protons and neutrons together within the nucleus, electromagnetism holds electrons in orbit, completing the atomic structure. It also enables the formation of larger molecular compounds, such as proteins, essential components of life on Earth. Beyond its role in nature, electromagnetism is fundamental to modern technology, powering everything from electricity generation to telecommunications, the internet, and radio transmissions. The force is carried by photons, a type of boson that differs from nuclear force mediators in a crucial way. They are massless. Unlike W and Z bosons, which have significant mass and thus operate over short distances, photons have no mass, allowing them to travel unimpeded across vast cosmic distances. They move at the ultimate speed limit of the universe, 299,792 kilometers per second, approximately 186,000 miles per second, known as the speed of light. But this isn't just the speed of light. It's the fundamental speed of the universe itself. It represents the upper limit for all forms of energy and information transfer. Any object with mass can never reach this speed, as doing so would require an infinite amount of energy. Photons, being massless, bypass this limitation and travel at light speed indefinitely, unless absorbed or scattered. The electromagnetic spectrum. Though individual photons are fundamental particles, they typically exist as part of broader electromagnetic waves. The frequency and intensity of these waves determine their position on the electromagnetic spectrum, which encompasses a vast range of radiation, from low-energy radio waves to high-energy gamma rays. At one end of the spectrum lie radio waves characterized by their low frequency and long wavelength. These photons are too spread out to be seen, making them ideal for transmission and communication purposes. Radio waves have been used for over a century, initially for broadcasting and later for television signals. Their ability to penetrate the atmosphere with minimal interference makes them essential for satellite communications, including GPS navigation, which relies on radio signals exchanged between space and Earth. Radio astronomy, which emerged in the 1960s, has revolutionized our understanding of the cosmos, revealing crucial insights about neutron stars, pulsars, and the remnants of the Big Bang itself, specifically the cosmic microwave background. This CMB signal resides in the higher frequency microwave bands of the radio spectrum. Microwaves, while similar to radio waves, have slightly shorter wavelengths, making them useful for weather monitoring, radar technology, and even medical applications, such as cancer detection and treatment. They also play a role in everyday life, perhaps most famously in microwave ovens, which heat food by agitating water molecules at the molecular level. Optical wavelengths. As wave frequency increases and wavelengths shorten, we transition from the radio spectrum into the realm of optical wavelengths, the portion of the spectrum that includes visible light. The first stop on this journey is the infrared band, a range of radiation that is particularly valuable in astronomy. Instruments like the James Webb Space Telescope rely on infrared detection to observe the most ancient and distant galaxies, whose visible light has been redshifted due to cosmic expansion. By capturing these faint infrared signals, Webb is providing us with some of the most detailed images of the early universe ever seen. Closer to home, most luminous emissions fall within the visible light spectrum. This narrow band of electromagnetic radiation consists of 7 distinct colors, from red to violet, with countless color variations in between. The visible spectrum is what allows us to perceive the world around us, making it one of the most significant aspects of electromagnetic interactions in our daily lives. From sunlight to artificial lighting, the role of visible light is essential, not only for human vision but also for photosynthesis, the process that sustains life on Earth. Beyond visible light lies the ultraviolet spectrum. Ultraviolet UV radiation is the most energetic form of optical light and is most commonly associated with sunlight. UV rays are divided into several categories, each with different effects on biological organisms. UVA, for example, penetrates deeply into the skin, contributing to cellular damage and increasing the risk of skin cancer. Despite its hazards, ultraviolet light also has important uses, including sterilization to fluorescence applications and medical treatments. From the longest radio waves to the shortest gamma rays, the electromagnetic spectrum paints a vast, complex picture of the universe. Each band carries essential information about the cosmos, helping us unravel its deepest mysteries. one photon at a time. Ultraviolet radiation and the ozone layer. UVB radiation is the main culprit behind sunburn, while UVC, the shortest and most powerful of the three, poses the greatest threat to life. Fortunately, most UVC rays from the sun are blocked by Earth's protective ozone layer, an ever-changing shield of molecular gas that continuously forms and breaks down under solar radiation. The thickness of this layer fluctuates with seasons, latitude, and variations in solar activity, with temporary reductions followed by natural recovery. However, in the 1970s, scientists discovered that human activity was severely weakening this protective layer beyond any natural cycle. A dramatic seasonal depletion of ozone appeared over Antarctica, traced back to chemicals known today as ozone-depleting substances ODS. These include CFCs, HCFCs, carbon tetrachloride, and methylchloroform, which were widely used in industry and household products. After being released, these substances take 2 to 5 years to rise into the upper atmosphere, where sunlight breaks them apart, releasing chlorine and bromine, two highly effective ozone destroyers. A single chlorine atom can obliterate up to 100,000 ozone molecules before it eventually leaves the atmosphere. This alarming discovery prompted international action, leading to widespread restrictions on CFCs and other harmful compounds. By the late 1990s and early 2000s, ozone depletion began to stabilize, and the Antarctic ozone hole showed signs of improvement. However, contrary to popular belief, the hole has never fully healed. Ozone depletion remains a concern, as some of these harmful chemicals are still in use, and new applications continue to emerge. This highlights the need for technological advancements that align with Earth's delicate environmental balance. Ionizing radiation. Advancing further into the electromagnetic spectrum, beyond UVC wavelengths, we enter the realm of high energy, ionizing radiation, powerful enough to strip electrons from atoms, which can be hazardous to living organisms. The first stop is X-rays. Also known as Röntgen radiation, X-rays hold a unique place in both medicine and scientific research. While dangerous in excessive doses, their ability to penetrate soft tissue while being absorbed by denser materials makes them invaluable for medical imaging, allowing doctors to examine bones and diagnose fractures. Beyond healthcare, X-rays are used in fields like archaeology, geology, and agriculture to analyze the composition of rocks, soil, and air. Due to their potential risks, their application is strictly regulated in most regions. Even more potent than X-rays are gamma rays, the most energetic form of electromagnetic radiation. Their photons are so densely packed that they can pass between atoms in a mirror, making them impossible to reflect or capture in the conventional sense. Unlike other forms of radiation, gamma rays are produced only by the most extreme cosmic events. On Earth, they are generated during lightning storms, in nuclear reactors, and during atomic explosions. In space, they are unleashed by supernovae, neutron stars, and black holes, painting the universe with flashes of light so intense they outshine entire galaxies. If human eyes could perceive gamma rays, the night sky would appear as a dynamic landscape of flickering bursts and luminous explosions. Some of the brightest sources of these rays are quasars, massive hyperactive galaxies, whose central black holes consume surrounding matter with such force that their light eclipses everything else in their host galaxy. The most violent gamma ray emissions come from gamma ray bursts, GRBS, the most powerful known explosions in the universe. These occur during supernovae, the collision of neutron stars, or the merging of supermassive black holes. In just a few seconds, a single GRB can release more energy than our sun will produce over its entire 10 billion year lifespan. If one were to occur close enough to Earth, it could unleash catastrophic radiation capable of devastating our planet's biosphere. Even neutron stars, the dense remnants of collapsed suns, can release gamma rays through powerful starquakes when their crusts crack under extreme pressure. These eruptions have been observed to leave measurable disturbances in Earth's ionosphere, even from 40,000 light years away. If such an event occurred within our cosmic neighborhood, the consequences for life on Earth would be dire. The forces that shape the universe. Thankfully, the nearest potential gamma ray threats are located hundreds or thousands of light years away, posing no immediate danger to us. Nevertheless, these powerful phenomena serve as a stark reminder of the immense influence that the four fundamental forces exert over the universe. Each force shapes different aspects of reality, governing the physical laws that define existence itself. Perhaps one day, scientists will discover the elusive graviton, the theoretical particle responsible for gravity, bridging the final gaps in our understanding of the cosmos. A unified theory of everything could finally reconcile gravity with the standard model, unveiling the fundamental principles that dictate the universe's structure. Until then, our knowledge remains bound by the limitations of current physics. Though the standard model has guided us far, it still leaves many unanswered questions. Only by solving these mysteries, especially those concerning gravity, can we hope to gain a deeper insight into the true nature of the cosmos. And with that, I bid you good night.